My name is Krzysztof Szczur and I'm Hardware Verification Products Manager at Aldec. In this presentation I'd like to share some ideas about RISC-V design and verification with FPGA hardware in the loop. The open source community has made a tremendous work to standardize the first truly open processor instruction set architecture called RISC-V. I would say that equal energy was given also to create first RISC-V microarchitectures using hardware description languages like System Verilog. Thanks to all these efforts, you can now choose from simple to very advanced and powerful RISC-V processors, and you can integrate them with your system-on-chip design. That's the easy part. But the system-on-chip verification is challenging. That's due to the complexity inherent to that type of designs. This complexity comes from the dual nature of system-on-chip, which is composed of hardware and software components. So let's talk about hardware first. Hardware part is a complex design by itself. Current designs are heterogeneous multi-core architectures with lots of subsystems and peripherals interconnected by hierarchical networks on chip. And traditional test bench methodologies based on directed tests cannot cope with this complexity. It's impossible to cover all functions with directed tests. Actually, it's not even possible to anticipate all possible real-life scenarios. So that's why constrained random verification methodologies like UVM were created, but the side effect is that they generate excessively long test sequences. As a result, simulation of such designs is very often too long. It becomes a bottleneck during verification. Formal verification methods were told to improve this process, but it turns they often give up due to the large space of system states. Now, it should be strongly said that some of the mentioned challenges could be addressed better if the hardware and software were verified together, but they are not. So these are the general challenges, but there are a few others related to the RISC-V open nature. So the open ISA and independent microarchitecture implementations require strong compliance testing of RISC-V cores. The RISC-V ISA is very flexible due to specifying optional functionality or instruction blocks. It also allows for custom extensions. So all this needs to be addressed during verification. And sadly, but this is the reality, that open source projects usually lack of comprehensive verification environments. So now let's look into the software domain. Software part is at least as complex as hardware. Actually, if we compare hardware and software by number of lines of code, we would clearly see that it's much more to verify on the software side. So even though many software components, algorithms and libraries are reusable, even if taken from unrelated projects, the reality shows that software integration and verification remains on the critical path of system-on-chip schedule. One of the reasons is that software developers need a fast and accurate hardware model, which unfortunately isn't available until late project stages. So the software developers have to use instruction set simulators, or if they are lucky, they can use virtual models of the CPU subsystem only. So software verification out of hardware context is the main disadvantage, and this is the main challenge in system-on-chip projects verification. And how important it is you can realize looking at the RISC-V available resources. So the ISS models, they only simulate RISC-V instruction set architecture. That's obvious because you can implement the same ISA in many different ways. For example, you can create a simple microcontroller level performance core, or you can create a high performance superscalar processor, and both will provide the same RISC-V ISA. The difference is in the microarchitecture, which is not reflected by the ISA instruction set architecture. Cycle accuracy can be found in the actual RTL code of the RISC-V core, but again, Verilog or VHDL simulators have orders of magnitude lower performance than expected by software developers. So the situation gets worse if the RISC-V core contains custom instructions, and the software toolchain has to account for that. There are some virtual models with higher accuracy. They can help in achieving microarchitectural level accuracy of the CPU subsystem. But then another problem comes in with the availability of virtual models of other IP cores used in the SoC. Now I have a good news. Hardware-assisted verification can help to tackle many of these presented challenges. Due to the availability of high-density FPGAs like Xilinx UltraScale US440 and their adoption for emulation, it's possible to hook these versatile devices into the verification environment and use them as a vehicle for implementing highly accurate SoC models. These models can be used for different verification activities throughout the entire project timeline. At the beginning, when RTL models are created and simulated, the FPGA board can be connected with the simulator. In this configuration, complex and long simulation sequences can be accelerated, and that's for the benefit of hardware design and verification teams. Migration towards hybrid co-emulation allows for system-level verification of the entire SoC. At this stage, the FPGA board can be connected either with the system-level test bench in the simulator or with the virtual platform or even with the external peripherals. So who will benefit from hybrid co-emulation? Hardware verification team receives a very fast model for running system-level regression tests. And the system integration bugs can be traced conveniently in the simulation-like environment because the same test benches are used during co-emulation. Now the software team receives a complete and accurate system-on-chip model to run their software and firmware components without compromising any functionality. If the firmware function needs to read peripheral register, it gets real data instead of fake or stubbed one as in pure ISS simulation environment. If the register value is unexpected, for example, now the software team can consult with hardware team to debug this case together. The bug needs to be fixed either in software or in hardware, and with hybrid co-emulation they are detected and fixed much earlier, and they can be corrected before the chip is taped out. Physical prototyping is the last pre-silicon verification stage. Again, the same FPGA board can be used to implement and run entire SoC hooked with external peripherals and devices. Prototype implementation is optimized for speed, and so it's capable of running a complete software stack, including operating system, device drivers, as well as top-level user or device main application. Hardware debugging is not concerned at this stage as the RTL is stable and frozen. Software last-minute verification and validation is the main task and the last one before the chip tape out. So summarizing, hardware-assisted verification is a significant improvement of traditional simulation-based verification process. It allows to sign off the chip with higher confidence and significantly shortens the bring-up process when the first chip production samples arrive to the lab. Now let me introduce Aldec HES-DVM, which is a complete hardware-assisted verification platform. With HES-DVM, you can reuse one FPGA board throughout all design verification stages, starting from simulation acceleration through emulation and closing the process with physical prototyping. Aldec HES-DVM platform consists of hardware, software, and reusable verification components. HES boards are state-of-the-art FPGA prototyping boards available in various form factors and in single or multiple FPGA configurations. Software components facilitate implementation and integration with users' verification environment and tools. DVM, which is part of the software component, is a design verification manager, and it's used to automate design setup. The bundle of verification environment interfaces allows for a quick and robust integration with many different verification environments and tools like simulators and virtual platforms. Reusable verification components is a library of commonly used transactors and monitors like AMBI-XI, USB, or PCI Express. And last but not least, hardware debugger. It provides comprehensive debugging features and improve productivity while debugging corner cases detected during emulation. So let's look into the hardware. Rich portfolio of HES FPGA boards contain single, dual, and scalable multi-FPGA systems. Aldec HES boards are built with the largest Xilinx Virtex 7, UltraScale and UltraScale Plus FPGAs. Single and dual FPGA boards are often used as desktop emulation for block level verification, but also for system level if used in co-emulation with virtual platforms. Desktop emulation is cost effective, so it can be replicated and shared across the corporate network, and that provides a convenient access to many hardware and software developers. On the other hand, multi-FPGA boards that additionally can be scaled up through the backplane, they are ideal for larger SoC designs, emulation, and prototyping. Apart from FPGA prototyping boards, we also provide many compatible daughter cards with peripherals dedicated for different applications, like Internet of Things, communication, automotive, and the like. For more information about the available boards and their specifications, please visit our website. And the last thing I wanted to say here is that you can also benefit from our experience in board design by ordering a custom board if needed for a project. So let's talk about the software components that come with hardware. DVM, which is Design Verification Manager software tool, it's for design setup automation. It will guide you starting at RTL source compilation through synthesis, partitioning, and FPGA bit file implementation. DVM provides two distinctive design flows, one for emulation and the other for prototyping. In emulation mode, that also includes simulation acceleration, DVM integrates verification interface with your design and provides behavioral compiler to convert transactors, monitors, and similar test bench components to FPGA. So your RTL code is compiled and converted to netlist using Aldec's fast synthesis engine. Then, in case of large designs that don't fit in a single FPGA, the netlist can be partitioned automatically into multiple FPGAs. If your design has ASIC-style gated clocks, they will automatically be converted to clock enables, and the user can also map non-synthesizable memories to FPGA or to external or onboard DDR resources. If you plan for in-circuit emulation, ICE, it requires connection to free-running clocks or external devices. DVM facilitates connection of such modules too. Important part of emulation is hardware debugging. During design setup, DVM tool provides source code instrumentation to preserve all required design internal signals and integrates the design with debugging infrastructure. The entire setup flow is incremental. So the incremental setup flow allows you to save the DVM project at any stage and reload it if required. That works even if you change design sources, so you don't need to recompile entire design, but only the changed modules. At the end of the flow, DVM also integrates with FPGA vendor tools to automate last stage, which is FPGA implementation. That's place and route and bitstream generation. You can also compile TCL script and you can create such a TCL script and use it in the future for further setup flow automation. FPGA prototyping has different requirements and objectives than emulation. That's why separate design setup flow is provided by DVM tool. The main checkpoints in the prototyping flow are synthesis, partitioning, connecting, and FPGA implementation. Basically the same as in emulation, but to achieve higher clock rates in emulation, the user gains much more control over the partitioning and interconnecting process. Like in emulation, every step can be fully automated, but the user can step in and modify the results or provide constraints for automation algorithms. For example, you can integrate your design partitions with the I/O serialization modules called interchip connectors, or ICC in short, or you can decide to provide your own implementation of ICC modules. It's also worth to mention that DVM prototyping flow is available as a separate tool or a bundle with emulation modes. The reason for having DVM prototyping separately is that it supports third-party boards. You can create your own board description file using System Verilog, and then with the board compiler you can import it to the DVM and finally use all the DVM powerful partitioning features exactly the same way as with Aldec HES boards. Going back to emulation, it's very important to have advanced hardware debugging capabilities to be able to trace corner case design problems that often show up at this verification stage. And HES-DVM provides such debugging capabilities that will make you feel comfortable even if you step on the mine that is a hardware bug. The first, static and dynamic debug probes extend your visibility space significantly and give you a choice between at-speed debugging or extended visibility. The HVD technology assures even 100% visibility, and the internal signals can be selected at runtime. Triggers enable automatic start of capturing debug probes, and breakpoints allow to stop emulation clocks under certain conditions. Full clock control provides determinism and ability to run design in single-stepping mode. The signals captured from FPGA are saved to waveform file from RTL names with RTL names. So you can debug your design in context of RTL code and design hierarchy. That's a very convenient way. And finally, memory visibility tool enables memory data upload or download at any time during emulation, which is a great help when running RISC-V or any other CPU that needs program and data memory blocks initialization or dump for debugging. The third software component, interfaces, are used to integrate hardware platform with the tools in the verification environment. Simulation acceleration interfaces contain support for Aldec and third-party simulators. There is also a choice of signal level and transaction level approach depending on the test bench, design and used methodology. Emulation and hybrid co-emulation are supported by transaction level interface, which is compliant to Axelera SCIMI standard. Additionally, Aldec provides System C and TLM wrappers to facilitate connection with popular virtual platforms. In-circuit emulation that often requires connection with external devices running at higher clock rates is supported by the speed adapter dedicated features in DVM, and also by support of multiple clock domains. And finally, there is a special interface for prototyping mode called HES-Proto-AXI. It provides speed-optimized host bridge and AMBA-AXI interconnection. It supports fast DMA and burst transfers, assuring high throughput data acquisition in prototyping test bench. The user can choose between C++ or Python API to develop test bench application. All the mentioned interfaces make a robust foundation in creating custom transactors and tailoring any kind of design under test with its test environment. There are, however, numerous standard interfaces like AMBA-AXI, PCI Express, USB, or JTAG, UART, and the like. To reduce the test bench development cycle, you can choose one of the ready-to-use transactors and speed adapters from Aldec. We can also develop a custom transactor upon request. Now let's review some examples of RISC-V design verification. Currently, there are 100 projects of open source RISC-V CPU cores and SoC platforms with the RISC-V core. There is, however, a verification gap between the open source fabless design and the one that is intended to be taped out. RISC-V core robust verification and compliance testing against RISC-V ISA is essential and should be done before you integrate the RISC-V core into your SoC design. And constrained random verification methodology like UVM works well in such case. You can develop a test bench that drives and monitors the RISC-V core RTL and also a reference model, for example, RISC-V instruction set simulator. The response of reference model should match the one from RTL implementation, so it's easy to implement self-checking test bench. Moreover, the UVM test bench can randomize sequences of processor instructions within the bounds set by user as randomization constraints. And here you can develop your own sequence generators or take advantage of open source project of RISC-V DV. Fixed test sequences can also be accommodated in such UVM test bench, which is useful when running RISC-V standard compliance test programs. Part of the test bench infrastructure are system bus transactors and monitors. In our example, standard AXI master transactor and custom-made trace monitor, they are based on Axelera SCIMI function-based interface and integrate very well with System Verilog UVM through DPI-C. And by using SCIMI, we achieve interoperability of UVM test bench, which now can be used either with design simulated or emulated in HES-FPGA board. Aldec HES-DVM allows for compiling RISC-V CPU along with some test bench components like transactors, monitors, and also clock generator into FPGA. Then you can use the same UVM test bench connected to design running in FPGA, and so you can accelerate the simulation tens or even hundreds times. I'd like to emphasize also that cycle accuracy is preserved in emulation, which is required for verifying microarchitecture functionality and benchmarking its performance. Let's take another example of emulation, which is the case of integrating entire SoC and performing system-level verification. Now, the emulation can be used either by a hardware team or by software team. Hardware team can use emulation to verify system-level integrity and requirements, as well as run regression tests after each update committed by developers. In this case, the idea of using or reusing system-level test bench for simulation and emulation is the same as before at RISC-V core level verification. System Verilog, the UVM or System C test bench connected with SoC design through scheme transactors enables deterministic test runs. In case of test failure, it can be debugged directly in emulation, or the failing test can be repeated in pure simulation environment. Next, the SoC emulation, if passed all the regression tests, it becomes a hardware platform for software developers. If the emulation was built with JTAG interface transactor, the processor can be now controlled from any software debugger. For example, popular OpenOCD debugger interface can be used to enable GDB debugger connection. So, hardware in the loop improves verification process, and this is how we help to integrate it with your DV environment. Building FPGA prototypes might be quite difficult and painful, but it shouldn't be so in emulation, where changes in the design are still quite frequent, and emulation needs to be rebuilt without too much efforts. That's why we support you with full design setup automation by DVM tool. FPGA-ready transactors development is facilitated by the DVM behavioral compiler, which converts non-synthesizable constructs to synthesizable form. Accelera scheme support guarantees that your transactors are reusable between simulation and emulation, but also across different emulation platforms and vendors. And hardware debugger enables convenient debugging of hardware in FPGA, in FPGA without returning to pure simulation environment. Now let's review hybrid co-emulation case. Let's start with defining a hybrid co-emulation term. Hybrid co-emulation is a mixed hardware-software emulation approach where part of the SoC is modeled as a virtual platform, and some other parts or subsystems are running in the FPGA emulation board. In our example, virtual platform contains RISC-V CPU subsystem along with some standard components which are available as virtual models and also interconnect. System C and TLM compliant simulators are typically used to model virtual platforms. And if other hardware models are not available, virtual platforms are quite willingly adopted by software developers at the beginning of software development process. However, some subsystems or peripherals, IP cores, are not available as virtual models, and in such case the virtual platform alone is incomplete and requires some dummy code to substitute for missing components. This issue is resolved by hybrid co-emulation. As soon as the custom subsystem is available in RTL code, it can be synthesized and implemented in FPGA. Connected with standard bus transactors like AMBA-XI or AHB, it can be integrated with the virtual platform, making a complete system-on-chip model that is now much better for software developers and for software development purpose. As an example of hybrid co-emulation, we have prepared a demo which connects OVP-SIM RISC-V virtual platform to the custom peripheral, which is a Sudoku puzzle solver hardware IP. The Sudoku IP provides AXI slave port, and so Aldec AXI master transactor was used to connect it with the software part in OVP-SIM. The OVP-SIM virtual platform contains RISC-V ISA model, RAM memory models, and also UART model. All these components are interconnected through TLM ports, and TLM decoder component is modeling the system bus. Using the same TLM interface, Aldec AXI transactor proxy is hooked, providing connection to hardware model of Sudoku IP. Please note that the same fixture is used for co-simulation with Aldec Riviera Pro Simulator and then to run emulation with Aldec HES boards. So first, you can test the connection and integration of hybrid model using HDR simulation, and then if everything works well, you can set up design for emulation and run design with hardware. Let me summarize a hybrid co-emulation case. If you decide to go with virtual platform, Aldec can provide you extended support of such hybrid co-emulation. Hardware model setup is fully automated by DVM tool, so you don't need to be an expert in FPGA. The HES board integrates with virtual platforms through standard interfaces, and Aldec provides AMBA-AXI and AHB transactors, which are very often applicable in SoC projects. The TLM wrapper makes them well integrated with any System C based virtual platforms. It's also worth to note that we support non-System C virtual machines, like for example QEMU. And finally, advanced hardware debugging enables tracing corner case problems between software and hardware. After co-emulation, the last verification stage is physical prototyping. Let me show you how it can be improved with Aldec support. Physical prototyping in FPGA is a powerful verification, validation and software testing platform that allows advanced hardware and software integration to be done long before chip tape-out. The prototyping environment requires FPGA board and several application-specific peripherals. These peripherals are available as extension daughter cards and can be connected with Aldec HES boards via standard and non-proprietary FMC connectors. Aldec also adds a host computer bridge to the board, which greatly simplifies test application development. The same host computer can be used to run software debugger, of course. And last but not least, Aldec DVM tool, which supports multi-FPGA design partitioning. It will significantly reduce time of prototype implementation and bring up. So this is a complete FPGA prototyping solution, and it contains FPGA boards along with peripheral daughter cards, has Proto-AXI host interface and design resources. and DVM automated design partitioning software. With this slide, let me conclude my presentation. So, as you could see, Aldec is a one-stop vendor for FPGA-based hardware-assisted verification. We provide simulation acceleration, emulation, and prototyping, and all of this using a single FPGA prototyping board.